Hello, we are live again. Today is November 18th, and it's like 10:53, which is kind of late. We need to get back on track and do these streams earlier in the morning, but today I just slept like 12 hours for some reason. I guess I was like in a lot of sleep debt. But today I want to finish up the VAE. So we did GPT last time, and although it was training, I guess like somehow it didn't train properly, so I guess I'll just train it again now. I'll train the VAE, the GPT. So while it's training, let's work on our VAE. So I have some starter code for the VAE, but it's essentially the same n in this data set, but here it's going to be data sets and data sets. So I guess to motivate VAEs, right? The first you have, it comes from autoencoders, and autoencoder is just another simple neural network, but we sort of like have two MLPs. One is an encoder, and one is a decoder. And the only difference is that this is a special MLP, is that the number of input features is greater than the number of output features for the encoder. So we're sort of like having to do, it's like a compressed low dimensional representation of the input. And then we have a decoder that takes this lower dimensional input and converts into some higher dimensional output. So that's the decoder. And the idea is that by going through this bottleneck, we have sort of like a very good compressed representation of the value, and we can actually use this as a generative model. So yeah, the encoder network essentially accomplishes dimensional reconstruction, and we simply have our losses are trained on reconstructing the input, and what that's going to force the network to do is to sort of like find a good representation. And our loss is simply given by an MSE loss, I guess, over the different pixels. But what the issue is that we face the risk of overfitting when there are more network parameters. Like one idea, I guess, is to just add Gaussian noise to prevent overfitting. And so they just sample without a bunch of noise, and they still try to reconstruct the noised, the input without noise. And then sparse autoencoder is like, you take some values within this lower dimensional representation. But the variational autoencoder comes more from a probabilistic idea, and the motivation is sort of like, instead of directly sampling from, I guess, do I have good images? Well, instead of like directly sampling from or like taking our encoder's input and then passing it to the encoder, we actually want to sample from the encoder. And so our encoder is going to be taking X, and then it's going to generate some latent representation Z. So Z is going to be sampled from, and here they talk about posterior and elbow, which I really need to review. So we sample Z from a prior distribution, and then value X is generated from given condition on Z, right? And the idea is that we want to find the set of parameters that maximizes the log probability of the correct data being generated, right? And I guess if it's a Gaussian, you sort of know the PDF until you know how to adjust it, right? So when they say it's not easy to compute p of data x this way, what do I mean? It's very expensive to check all positive values of z and sum them up, right? Like, what is the latent representation given input parameters 5? Right. I guess, so the way Lillian was trying to explain this is from first the decoder perspective, right? So we want to find a generator that takes some input z and maximizes the probability of getting a target value x. But searching over all possible spaces of z is really expensive. And so rather what we can do is introduce another, like a generator or the encoder. Sorry, I'm mixing my words. We can sort of like, I guess this is another generator to facilitate the process. And this is parameterized by q of z given x, but you're not given, I guess you're given, yeah. I guess, what do you call these? The, I mean, it's the encoder and but they're both basically generators. One generates x and one given z, and one generates z given x. And one of them is the likelihood. Likelihood is probably of seeing data given your parameters, whereas posterior is probably of your parameters given the data. So once you've seen your data, what is the probability of you seeing your parameters? And the conditional probability defines generative model. Now, we want to minimize the KL divergence, that is the probability distribution between our these two distributions. Okay. Right, because the generator is p of x given z, but we want to minimize p of x given z, so I guess we can use, what, Bayes' rule? So we sample, one of them is the sample z. Yeah, I'm not following this part. Right, so we said we want to find a set of parameters that can generate x, right? And so we can expand this out. It's conditioned on z, and so we want to maximize this. And so we essentially, it's very expensive to search over z, so we're like, okay, what we want to find a generator that can generate this latent space given x, and what is a likely code given input x? And this, okay, now where does this come from? P of theta z. Like, what does this freaking mean? What is this? Okay, I guess what this is saying is P of theta x is equal to P of theta z times P of x given z, right? That's just like conditional probability, right? So P of AB times PB is equal to P of A and B, not P of A. Okay, so no, so that's not what it is. Yeah, I guess if you sample from Z, you get this value Z, and then you can compute P of x given Z to get x, right? Because you're conditioning on Z. If it's not conditioned on Z, then you just get the probability of x. And I guess that's what it's saying. And so the generative process is Q of phi z given x should be approximately equal to P of theta z given x. Because at inference time, what's happening is we have P of x given z, and then Q, no, is it P or Q? It's Q of z given x, and then P of x given z. Because P theta z given x is intractable. That's us, chat. Yeah, like, okay, really what we want is to learn a probability distribution over our data, right? So that we can sample from it and get x, right? But to maximize this probability distribution, you sort of like compute it over the marginal probability of z, and so you get this equation, right? This is the marginal probability. That's just summing over all possible values of z, right? That's just like how you formulate it. But this equation is intractable because there are a lot of values of z, and you simply cannot make this tractable. And so rather, what you can do is make this problem tractable by conditioning it on Q like I just don't know yet. Why is it called a variable? You're doing variational because you're optimizing over distributions as opposed to parameters directly. As, like Z is also sampled from some distribution. Is it that... Okay, let me try to explain this to you and you tell me... Okay, let me try to explain this to you and you tell me if I'm understanding this correctly. Essentially what we're trying to do at first is we have P of X. We're trying to learn P of X, right? The probability distribution of X. You know, assuming X is sampled from some probability distribution. And so the way we sort of like learn this is we condition it on some latent variable Z, right? So we say like, we want to, we say that we first sample from Z and then condition P on Z, right? And our goal is to essentially maximize the probability of P of X, the log probability of P of X given where X is sampled from like our distribution, right? And so if you expand this out, it's going to be the marginal marginal probability, right? So you have P of X given Z is equal to the, P of X is equal to the integral of P of X given Z times dZ, right? P of X times Pz dz. And we're saying that this is intractable because P of Z, there's just like too many different Z's to try. And we're saying Z here is also some other probability distribution, right? So there's an infinite amount of probability distributions to try out. And so therefore what we're going to try is we're going to actually use another function to approximate this distribution. And this is why I'm getting lost, where like the chain of thought is like I'm getting confused. All right, yeah. Yeah. Like P of Z is already known. Or P of theta is some known distribution. Why do we need the posterior? Because The posterior is also intractable. And why is it intractable? Because of PZ of x is P of x. But like, what about P of x given Z? Right? Why is P of x given Z tractable? I guess it's just conditioned on Z, right? So like, it's a mean of x I don't know what this, there should be two numbers. F of x given z is tractable because we're just saying this is a function we learn. So it's very easy to compute it. Got it. Okay. So we have P of x and P of x is not tractable because we need to, like P of z is tractable because we're saying we're just sampling, this is like defined by us. And P of x given z is also tractable because we have a neural network learn that, right? But P of x is unknown. have p of x is equal to the int p of x. Like, what does this mean? There's no closed form. I guess, how do you do integrals over probability distributions? This is Gaussian. Not Gaussian as a function of z. Least amount was on half x minus mu over sigma squared. Okay, x minus mu. Okay, that's where it's coming from. Okay, let's see it. like if you expand it out, P of x given z, that's going to be a neural network with a bunch of computations, and you're integrating it. The integral makes things very hard, I guess, right? What are closed form solutions for integrals? Yeah, integral is a closed form. So what do? Because there's no closed form solution, we can approximate this. We approximate variation. Is this correct? That's not elbow, actually. So fucking annoying. I know there's a KL divergence which uses it's a regularization. I'm just trying to understand how you freaking derive this shit. I'm trying to fucking intuit this. Oh, it's excitation. Um, right. Got it. Oh, that's stuff. Okay. Surrogate loss. Fuck. I just understood it, and I don't understand this chain of thought, man. Freaking up. What was my chain of thought? Like, I understand this. Okay, I understand. This was okay. It's intractable. So what do? We approximate maximizing log probability of this. Right, like we want to maximize this log probability, and so if we maximize this, we're saying x motivation worst case. It guarantees the worst case of the likelihood. Like, I don't understand what that means. The log probability of this data is greater than some I guess that's the sum of the probabilities needs to be 1. guys, so annoying. I need to understand this. If you don't understand this, you're just gonna write stupid code and just implement the objective, but you have no intuition. How do you go to sleep though? Frick. Alright. Need to spend a bit more time. I hopefully though, you know, understanding this gives you a lot of intuition on and ideas on how people have done things. And VQ-VAE is essentially building on top of this variational inference. Isn't there yeah, I was reading this. Yeah. Honestly, the person who came up with VAEs is pretty smart. Okay, I'm gonna wrap it up here.